Alright, this is example 1 in module 9. We have a picture that shows 3 different currents. They're all long and straight and parallel. We have a head-on view of these currents. So current 1 up here is pointing out of the board, current 2 is going into the board, and current 3 is coming out of the board. And what we're supposed to do is find the net magnetic field at this observation point up here. We're told that all 4 of these points are on the corners of a square. So they're all the same distance apart. And then we need to find what the magnitude of that magnetic field is and what the direction of that magnetic field is. So the first thing I'm going to do is I'm just going to draw sort of a diagram that shows the magnetic field from all 3 of the currents separately so that we can see what they look like, and then we need to add those together. So the first thing that we need to do is figure out the direction of these magnetic fields. So if I look at the magnetic field due to current 1 at the observation position, I need to use the one of the right-hand rules to determine what the direction is going to be. So let's say I've got a current that comes out of the board like this. The right-hand rule to determine the direction of the magnetic field is to point your thumb in the direction of that current, and then your fingers curl around the current in the direction of the magnetic field lines. And the magnetic field lines are going to be circular. So we have circular lines. If I point my thumb out of the board, my fingers curl counterclockwise, so these magnetic field lines are going to point counterclockwise. Now, if I go to the right of this point, right here, the magnetic field vector at that point then is going to point up. So that's what we have for current that goes out of the board. For a current that goes into the board, it's just going to be the exact opposite. Again, I would apply the right-hand rule. So here I have current that goes into the board, point my thumb into the board, and my fingers curl clockwise around the current. So it's still going to be circular magnetic field lines, and they're going to point clockwise. And now again, if I went to the right of this current, the magnetic field vector at that point straight to the right would point down. Alright, so that's what I need to do for all 3 of these currents. So let me draw a plus sign here marking the observation point, and look at the magnetic field due to current 1. So I point my thumb out of the board, my fingers curl around the current in the counterclockwise direction, so at the observation point the magnetic field due to current 1 would point in this direction, points in the plus y direction. I guess we also have a coordinate system that is shown on the figure. So this is B1. Let's do the third current before we do the second current, because that one will be a little bit simpler. So the third current, point your fingers out of the board, your thumb out of the board, your fingers curl counterclockwise. So we're going to have a magnetic field vector that looks like this due to current 3. And for the second current, we need to point our thumb into the board and our fingers curl clockwise. So we're going to have a magnetic field vector that points like this due to current 2. So now let's write down the magnetic field due to each of these currents, and then we're going to have to add them together. So the magnetic field strength, we know how to calculate what the magnetic field strength is. We have a formula that tells us the magnetic field due to a long straight current is just mu naught, which is the permeability constant, times the current over 2 pi r, where r is the distance away from the current. So we just need to apply this formula for all 3 of the currents. So for the magnetic field due to current 1, it's going to be simple because it just points in the y direction. So the magnetic field strength, current 1, if we look at the figure, current 1 is a distance L away from the observation point. So its magnitude is going to be mu naught I1 over 2 pi L. And its direction is in the plus y direction. So we put a little y hat there. I'm going to do current 3 before I do current 2 because it's also going to be fairly simple. Current 3 produces a magnetic field that points in the negative x direction. So the magnetic field vector is going to have a magnitude. Again, it is a distance L away from the observation point, so this is going to be mu naught I3 over 2 pi L, and that is in the negative x direction. So I'm going to put an x hat here and a negative sign out front. And now we need to figure out what the x and the y components of the magnetic field due to current 2 is. Let me just draw an angle here so that we have a reference. We'll have to figure out what this angle is. But if I knew that angle, then the magnetic field due to current 2 could be written as the magnitude of the magnetic field due to current 2 times the x component would be for the angle that I have drawn here, it would be the adjacent side here. So that would be cosine of that angle. That would be times x hat plus the magnetic field magnitude times sine of that angle. That would be y hat. But note that the vector here points down, so I need to put a negative sign for that y component. So if I calculated what the magnitude of the magnetic field due to current 2 was, then I could multiply by cosine of this angle to get the x component and sine of this angle to get the y component. So the two things that we need to do are calculate what the magnitude of that field is and what this angle is. Let's do the magnitude first. So we just need to figure out how far current 2 is from the observation position. So I have current 2 here. There's a distance L here and a distance L here, and then here's my observation point. So what I want to do is figure out what the length of the line that connects current 2 to the observation point is. So I'm just going to use some trig here. So basically I have a right triangle that has a side length of L, and I want to know what the length of the hypotenuse is. So R is just going to be L squared plus L squared square root of, which is going to give me L times the square root of 2. So that's how far away the current 2 is from the observation point, which means that the magnitude of the field due to current 2 is just going to be mu naught I2 over 2 pi L square root of 2. Alright, so there's the magnitude. Now we need to figure out what this angle is. Well, we really just need to know what cosine of the angle and sine of the angle is. But let's figure out what this angle is going to be. So if I draw a picture of the direction that the magnetic field is going to have to point due to current 2 at the position of the observation point, I note that the magnetic field lines are going to form circles. So if I draw, the center of that circle is going to be current 2. So if I draw a line from current 2 to the observation point, then the magnetic field vector points down and to the right, and it makes an angle of 90 degrees with that line that connects the observation point to the current 2. So I can use this fact to sort of figure out what that angle is going to be. So let me draw some horizontal and vertical lines here. Okay, so here's a horizontal line in the x direction. Here's a vertical line in the y direction. I want to figure out what this angle theta is. Well, let's go down to the current and draw a horizontal line. This angle here has to be the same as this angle here, which has to be the same as this angle. So this angle is theta, this angle is theta. I know what the length, if I just use the geometry of the problem. This is a length L, this is a length L. So theta is equal to 45 degrees. Now cosine of 45 degrees is actually equal to sine of 45 degrees. And those are both equal to the square root of 2 over 2. So that means that I can write the magnetic field due to current 2 as its magnitude, which is mu naught I2 over 2 pi L square root of 2, times cosine of 45 degrees, which is going to be the square root of 2 over 2, that's times x hat, and the x component should be positive, the y component should be negative. And sine of 45 is also the square root of 2 over 2. So I have a square root of 2 in the numerator and the denominator. Let me just simplify this a little bit. It's going to be over 4 pi L, and that should be a negative sign. There we go. All right, so we have our 3 magnetic field vectors now. I have written them in vector form, right? This has a y component, this has an x component, and then B2 has an x and a y component. So we need to add these vectors together. Now to add vectors together, we just need to add all of the x components together, and that will give us the x component of the net. And then we add all of the y components together, and that will give us the y component of the net. So I'm just going to draw a little table here to do the addition. So first I'll do the x components, then I'll do the y components. So for B1, its x component is going to be 0. So B1 has an x component that is 0. For B2, its x component is right here. That's going to be mu naught. Now we are told, which I haven't used yet, but I'll do it now just so that it'll simplify things when we add these together. We are told that I1 is equal to I2 is equal to I3, which is equal to I. So all of the currents we can just write as lowercase I. So this is going to be mu naught I over 4 pi L. And then current 3 has a negative x component. And again, I'm going to replace I3 with I. So there's the x components. Now let's look at the y components. B1 does have a y component. Its y component is positive. B2 also has a y component. Its y component is negative. And B3 does not have a y component. All right, so now to get the net, I'm just going to add all of these together. So let's see here. I've got a mu naught I over 4 pi L minus a mu naught I over 2 pi L. If I multiply this by 2 over 2 so that I have the same denominator, then I'm going to get a negative mu naught I over 4 pi L when I add those two together. Over here, I'm going to get a plus mu naught I over 4 pi L when I add those two together. So here we have the x and the y components of the net magnetic field. So the question asks us, or we're asked to determine the net magnetic field. That would mean to write it in vector form, either as a magnitude and direction or in component form. I have the components, so I'm just going to write it in component form. We're going to have to determine the magnitude and direction in the next parts. So let me write the net magnetic field as a vector now. This isn't the magnitude. As negative mu naught, that's not a very good mu naught I over 4 pi L times x hat plus mu naught I over 4 pi L times y hat. All right, there it is. There's the net magnetic field.